So in this video, we're going to try tackling two more examples of dealing with adding up an infinite number of vectors and trying to find the net, or in other words, the resultant vector from adding up all those vectors. So let's try example 4. So in example 4 here, we have a ring of uniform linear charge. It's uniformly charged, of uniform linear charge density, which basically means that there's the same amount of charge per unit length, or in other words, the same amount of charge per meter. So if I was to grab some like this arc of charge, right, so like something like this, where if I took some arc of charge on this side and then anywhere else where I took the same length of charge, maybe like that on this side, these are both going to have the same amount of charge. That's all that we mean by uniformly charged when we're talking about linear charge density. So in this example, what we're going to try to do is find the net electric field vector at the center of the ring at this beige point that I've drawn here. And so what we want to do, and this is how we've tackled many of the other examples like this, is we want to consider slicing up this charge distribution into an infinite number of infinitesimal amounts of charge, into an infinite number of infinitely small amounts of charge. And we're going to call each infinitely small amount of charge a dq. So let's try picking a dq over here. Let's just say, this is one infinitesimal amount of charge. So this is that dq. And to help visualize what the net electric field vector is here, we're going to pick another dq on the opposite side of the ring, right? So let's pick this dq. So this is some other infinitesimal amount of charge. And let's try drawing the electric field vectors due to each dq at this point. So electric field vectors, they point away from positive charge. So the electric field vector due to the dq on the left is going to look something like this, right? Something like that. And then if we draw it for the dq on the right, we end up getting something like this, right? Something like that. Actually, it's supposed to have a little more length to it. So something like this, right? I don't know if that was longer. They're supposed to have the same length. I'm trying to make them have the same length. So let's try this one last time. There we go. Something like that. Right, so they have the same magnitude, but just opposite direction. They have the same magnitude because they're, both infinitesimal amounts of charge, so they technically are the same amount of charge, and they're also the same distance away, right? All the points on a circle are the same distance away from its center. So their electric field vectors are going to point in opposite directions, but have the same magnitude. And then we can pick two more DQs to try to see a pattern, right? So let's pick, I don't know, maybe a DQ over here. Let me stop drawing straight lines. Let's pick a DQ over here, right? DQ. And then we draw its electric field vector, and it points something like this. They're all supposed to have the same magnitude, right? And then we can pick another DQ. Let's say we pick one right over here, directly opposite, right? Another DQ. And its electric field vector points like this. And so what we see is that as we go around this ring and imagine DQs on opposite sides of it, that their electric field vectors cancel each other out, right? If you were to add the green and cyan or turquoise vectors here, electric field vectors, you'd see that, they sum to zero. They just sum to a point, right? And the same thing for the magenta and orange vectors here. They sum to zero. So, and you can go around the entire ring and do this, and what you find is that for every DQ on one side of the ring, there's another DQ whose electric field vector at the center of the ring is going to cancel its electric field vector. So we end up finding that the net, or the resultant electric field at the center of this ring of uniform charge density that's uniformly charged, is actually 0, right? So E here, the net E at the center is 0, right? So, and then let's try one last example here. And here what I've done is I've taken the ring, right, that we had up above, and this again is uniformly positively charged. So again, you can imagine these plus signs going all the way around it. But instead what we want to do in this example is we want to look at it in 3D. So we've kind of tilted it a little bit, and the positive y-axis is going perpendicularly through its center. So it's got an angle here, right, that's 90 degrees. So the ring itself lies in the xz plane, and the positive y-axis, or the y-axis, is coming perpendicularly out of the ring. And I'm trying to draw a right angle here, something like that, right? It's coming, or I can draw it on this side too. It's coming directly perpendicularly out of the center of this ring. So what we want to do is we want to find the net electric field vector at some point along the y-axis. It can be the negative y-axis, but we're just going to focus on the positive y-axis here. And we already found that the net electric field at the center of the ring, at this base point here, is 0. But what we want to do is find it at some point along the positive y-axis. So what we want to do is we want to imagine slicing up the ring into DQs again, into an infinite number of DQs, and imagining what happens with their electric field vectors at this base point, and trying to see if a pattern emerges, if the vectors cancel each other in a way, or maybe their components cancel each other in some way. So we're going to try a similar tactic to what we did up above. So what we're going to do is we're going to, let me just pick a color I haven't used yet on this ring. So we're going to pick DQs that are opposite each other on this ring and find their electric field vectors at this base point. So let's pick this DQ, and then going along the x-axis, we're going to go to the other side, and let's pick this DQ. I think it would be about here. If we imagine extending this axis to all the way through the ring, I'm imagining this is where it would hit the ring, something like this. So we've got another DQ over here, right? And let's consider their electric field vectors at this base point. So for this magenta DQ, if I'm going to try drawing this dotted line just to help imagine where it's supposed to point, and then it ends up pointing something like this, right? Something like that. And then let's try doing it for the green one. So we come over here, and again, these dotted lines and their vectors for these two DQs both lie in the XY plane. So this vector might look like it's pointing upwards. It's not. It's supposed to be giving the sense of distance, of pointing kind of away from us slightly. So, and then we draw this DQ, or this electric field vector due to that DQ. And again, both lie in the XY plane. And looking at them, the angle here, right, we could call it theta or whatever we want to call it, is the same angle as this angle over here, right? Because you can imagine this, right, this axis is coming perpendicularly through the center, and if you imagine, like, your eye is over here or something, right? Something like this, and you're looking down the, and maybe you've got like some eyelashes or something going on, and you're looking down the positive y-axis. You see both vectors are the same angle. One's pointing a bit to the left from the positive y-axis, and another one's pointing a bit to the right. So let's try picking two more DQs. So let's pick, I'm just, again, trying to find a color. Let's pick one at the top of this ring, right? I've been going like this, actually. So this is one DQ, and then let's pick one in dark blue on the bottom here, another DQ, and let's draw their electric field vectors. And I don't want to draw too many dotted lines, but we imagine coming down, and then this electric field vector, due to that yellow DQ, is going to point something like this, something downwards, right? And then this DQ is going to have its electric field vector point up, something like this, right? Right, so something like that. So what we end up noticing is that a component of either electric field vector ends up canceling. So before I actually draw these two, let's talk about what happened with the green and the pink vectors here. So notice that the y components of the pink and the green vectors ended up adding, right? So if we were to draw the components of each of them here, and I'll just use, what color do I want to use? Let's use this color. So, right, this is like the x component, and then this is the y component, and then this is the x component, and then this is the y component. So what we see is when we add these two vectors, right? And they've got like right angles here going on. When we add the pink and the green vector, their y components both add, right? So we get like this, and then we get another something like this. But their x components cancel each other out, right? The x component of one goes like that, and then the other one goes like that. And so these two vectors end up canceling each other, whereas these two vectors end up adding. So just looking at the green and pink vectors, we end up seeing that their net, their resultant vector ends up pointing something like this. Their net electric field vector ends up pointing something like this along the positive y-axis. So that's for the green and pink vectors. But if we could, now let's consider these two DQs. So, right, so it points something, I'm going to try to draw a straight line. So it points up somewhat like this, something like that, right? And I can't even hardly see that. Let's use this blue. Maybe this is slightly better. So we pick this, this color for that, and then I use this yellow. So coming down, this electric field vector is going to point something like this. I don't know. This perspective isn't working out super well. It's going to point something like this. And then the blue vector. Yeah. Okay. So what we end up seeing is that if you look at the yellow and blue vectors, right? So the yellow and blue vectors both lie in the YZ plane. And looking at those two vectors, and I'm sorry, there's kind of a lot going on here, but if you just try to imagine this yellow vector and this blue vector, their Z components end up canceling each other out, right? So if I was to draw their components, right? So I've got the blue vector going on here, right? Something like this, and then I've got the yellow vector coming something like this, right? And so and then we've got the y-axis coming along through here, something like that, right? So these two angles are the same, right? This angle is the same angle as this angle, and this is the positive y-axis that we've got going on here. Then we've got the positive z-axis, and then we've got the positive x-axis going on. So I'm just imagining this beige point right here. So their z components end up canceling each other, but their y components end up adding. So due to the blue and yellow vectors, their net resultant vector ends up looking something like this, of just another electric field vector that points along the positive y-axis. And so what we end up seeing is, as we go around this ring and we just consider DQs on opposing sides, right? The component of their vectors that is perpendicular to the positive y-axis they end up canceling each other out, right? In this case, the perpendicular component is the x component of either vector. For the blue and yellow vectors, the perpendicular component, the component that's perpendicular to the y-axis, ends up being their z component, right? So what we end up seeing is that, as we go around the ring and we imagine all of the DQs on the opposite sides of the ring, that the net resultant, the net electric field vector, the resultant electric field vector at this beige point is something like this. And I'm going to draw it, it's something like this. It ends up actually pointing along the positive y-axis. So of course you could draw it here. I'm just trying to make it slightly less messy. So this ends up being our net E, right? Our net electric field at this beige point. So at this, at some point along the positive y-axis, the net electric field due to this ring that's uniformly charged is just some vector that points along the positive y-axis. So again, I hope that was helpful. And imagining, slicing up these charge distributions into infinitesimal amounts of charge, into DQs, and then imagining the electric field vector due to each DQ, and then seeing if some pattern emerges of how their components cancel each other out, or how the vectors cancel each other out.